When we take data, it's often helpful to represent that data in the form of a graph to make it make more visual sense and give it some organization. So there's many different types of graphs we can use depending on how we want the data presented and what kind of data we're working with. We're going to look at a couple of examples of graphs and then how to create our own. So this is the first type of graph that we're going to look at. As you can see, this is some favorite sports of students that are in the 5th grade. And what type of graph would you call this one? This is a bar graph. So you can see the little bars here, and the little bars tell you how much. So bar graphs just tell us a quantity of different variables. But when you see a graph, I want you to think deeper. Are these 5th graders in Texas? Well, probably not, because you don't see what? Football. Are they in the north? Well, there's no hockey, so possibly not. Are they female? Are they male? You can really look into the graph and try to discern some things about the data beyond just 25 kids like baseball. So there's that surface level information, and then there's deeper information that you can gather by interpreting the graph. Here's another one. What would you call this graph? This is a pie graph or a circle graph about pie. So pie graphs or circle graphs tell us a percentage of the whole. What percent of everyone surveyed like pumpkin pie? What percentage like apple? Which one do they like the most? The one that's enjoyed the most would have the biggest piece of the pie, right? But does it tell you anything about the people? Are they perhaps from Texas? Pecan pie is way too small if they're from Texas, right? Does it tell you if they're male or female? Does it tell you how many people? Was this out of 100? Was this out of 1,000? So there's deeper data that you can glean, that you can interpret, and some data that's like the number of people surveyed, that's just not present here. What kind of graph is this? This is a line graph. Obviously, there's the line right there. And line graphs are helpful for telling you how things have changed. So this is Amanda's trip to Washington, D.C., and what has changed is where she's at, her position. Now, again, there's deeper level stuff that you can interpret, not just, oh, at 9 o'clock she left her house, but you can also get some information about maybe what happened between 11 and 12. Well, her position didn't change, perhaps between 11 and 12. She stopped for lunch. That's what a lot of people do at that time. You can tell a little bit about where she was going faster, where she was going slower, and where she wasn't moving at all. You notice between 2 and 2:51, the line is a little shallower. It doesn't have such a steep slope. During that time, she was going a little slower. What do you know about Washington, D.C.? It's an urban area, so she probably got into some traffic. You can also possibly even look and tell where Amanda's from. If you know that she had to travel about 275 miles to get to Washington, D.C., maybe you could draw a little circle around Washington, D.C. at 275 miles and see perhaps some possibilities of where she lives. So think deeper than just information. Think about what you can gather from those graphs. When we're graphing, especially in physics, we're probably going to use line graphs because we're going to be looking at how things change. Multiple things will be changing, and those things that change in our experiment are called variables. Now, we have some variables that change on their own, or what we as the experimenter change. So things like time changes on its own no matter what experiment we're doing. So that's always going to be what we call the independent variable. The thing that changes as the result of the independent variable changing, so as time goes by, our population increases, that's the dependent variable. That value depends on how much time has gone by, or maybe if we're looking at the acidity versus the concentration, perhaps the more concentration of an acid we put into our solution, then the pH changes. That it would be the dependent variable because it depends on what we did. When we look at the relationship between our two variables, sometimes we get linear relationships and sometimes we don't. Now, linear relationship means that there's a straight line. There's a direct proportion between the two. And you've worked with these before. You remember this old equation y equals mx plus b? The slope will tell you the ratio of change between your vertical, which is your dependent variable, and your horizontal. So slope is rise over run. That's how much our dependent variable changed versus how much our independent variable changed. And then, of course, the y-intercept is where we started. That's where we cross that y-axis. We've got two relationships that we might notice when we've got direct relationships. We've got a direct and we've got an inverse. Direct would be like the one on the right there. If you have more income, then you're going to buy more things. Your consumption goes up. That's direct. They go up together, or they may go down together. Inverse means as one goes up, the other goes down, kind of like a seesaw. That'd be your inverse relationship. So in this case, as the basketball ticket price increases, less people can afford to go to the game. That would be inverse. One goes up, the other goes down. Here we've got a line graph that shows two cars that are moving. So you see their distance, their position over here is changing as time goes by. Now, a couple of questions here. One, why are they both labeled car number one? But anyway, we're going to call them the red car and the black car. And two, which one of these cars won the race? Which one got to the end first? It looks like, at first glance, that this red car is out front. But think about what the graph is telling us. It's not telling us just the position. It's telling us the position with time. So if the finish line was here at 5 miles, that's where the black car stopped. Who got there first? Right here at 8 minutes, the black car arrived at 5 miles. The red car didn't arrive until minute 9. What else can you discern with these two graphs? What do you know about the black car's motion if it's a straight line? If it's a straight line, that rate of change of position is staying the same. It's going the same speed. It's on cruise control, so to speak. What about the red car? What's it doing? Well, it starts off with a very low slope. You notice the slope is low down here. We're not changing a lot of distance in the amount of time that's going by. Towards the end, it's a lot more steep. We're changing a lot of distance in the time that's going by. So if we're not changing much distance in time, it's going slow. If we're changing a lot of distance in the time that we've got, then it's going fast. So this car sped up. It started off slow and then increased its speed as the race went on. So it's kind of a tortoise and a hare scenario here. When we make our own graphs, whether we are graphing our own motion or the momentum or the forces that are occurring, there's a couple of steps you want to take, and you want to put these in your notebook. First, you identify what's going to be your independent and your dependent variable. This will be easy if you have time. Time is always independent. It's going to do its thing no matter what we're doing. But your independent will go on that x-axis, the horizontal axis. Your dependent will go up and down on the y. Determine what range you're going to need. Will you need to go from 0 to 100 or just 0 to 10? How much data are you going to need here? Decide whether you can start at the origin, 0, 0, or maybe in the case of years that have gone by, you don't need to start at year 0. You need to start at year 1940. Where do you need to start your data? Spread your data out as much as you can without running off the page, and let each division on graph paper stand for some kind of convenient unit. Count by 5s, count by 10s, whatever you need to do to get it to all spread out and fit. Then do the same with your horizontal. With the vertical, your dependent variable. Then plot your data points. And if you are connecting them, connect the dots. If you've got more like a scatter plot, you want to draw your line of best fit that fits through as many of those data points as possible and gives you that relationship. And then make sure you label and title your graph. You want to make sure you label if it's time or if it's distance or if it's, motion of a car. Make sure you have those labels on there so you know what your graph is all about. Okay, so that's a quick refresher on graphing. Today we're going to make a graph with the data right here in this classroom.